Hello, good morning. Myself Jagendra Singh. The title of my paper is A Novel Approach on Reinforcement Learning for Improved Throughput in Power Restricted IoT Network. Paper ID is 502. So, in the abstract, the rapid expansion of Internet of Things has stressed the importance of energy efficient communication protocols, particularly in networks operating under power constraints. This paper presents a unique approach for managing communications in energy limited IoT network using a deep reinforcement learning based communication protocols by integrating sparse code multiplexes, code division multiplexes techniques, and combined experience replay deep deterministic policy gradient algorithm. We develop a novel protocol to improve the throughput of power constraint sensors in IoT network. Through comprehensive simulation, we compare the proposed protocol performance with benchmark systems like traditional DDPG and stochastic algorithm. The result reveals superior energy efficient and throughput with the proposed protocol, establishing its potential to signify enhance the performance of energy constrained IoT network. In introduction part, the Internet of Things has had an impact on numerous industries, including transportation, healthcare, and others. The Internet of Things potential to globally connected billions of devices ranging from simple sensors to sophisticated machineries. It revolutionizes how data is acquired, how data is processed, how data is utilized for informed decision making. So one of the key aspects impacting the success of efficiency of IoT is the communication protocol used within the network. So protocol for communication are crucial, especially with the emerging of IoT 4.0 and the consequences expansions of industrial IoT because these networks usually operate under power constraint. They really large on sensors to allow communications. Traditional communications method struggle to manage such energy constrained devices. Therefore, IoT network function poorly. So the sparse code multiplexes and code division multiple access algorithms were introduced as a critical first step in resolving the issue. These technologies, when combined, have successfully enabled autonomously sensors to communicate effectively over the internet. Other part of for this introduction, this research describes a novel use of DRL in the design of communication protocols for IoT networks with restricted energy resources. It is a novel ideal to combine the SCMA method, CDMA architecture, and the CDDPG algorithm into a single protocol through detailed simulation results and performance evaluation. This study will demonstrate the benefit of this method and provide significant insight into improving the performance of energy constrained IoT networks because many IoT devices have limited power. IoT networks require communication protocols with efficient energy management, although standard protocols like a Zigbee, LoRaWAN, and Sigfox are widely utilized. Each has advantage and disadvantage over to the IoT applications and locations. So the fundamental issue with it application, however, is energy efficient. As a result, finding more energy efficient communication protocol for network has become a critical topic of the research. So the system model for this proposed approach is architecture of a limited energy IoT network. Sensors, actuators, and the gateway that connect it to other networks such as internet are typically found in devices in an energy constrained IoT network. These elements interact with their surroundings, sensors and actuators often known as devices, are typically powered solely by batteries. The wireless connections modules in these devices allow data transmission and reception as displayed in figure 1 in the paper. So a typical Internet of Things network with limited energy resources is made up for thousands, if not millions, of these devices spread across a large geographical area and linked to one or more gateways. So the device is connected with the gateway and with one another using low power wide area network protocols. These networks necessarily communicate with systems that can efficiently manage data flow while preserving the device short battery life. So the communication protocol overview after the first one, this study proposed communication protocol incorporates a DRL algorithm, the CER DDPG techniques, the CDMA framework, and the SCMA methodology. The SCMA technology is employed in this protocol to ensure that the transmission of the power restricted autonomous sensors occurs during the time slot of a licensed sensor. The CDMA foundation allow the network many sensors to communicate more rapidly. The CER DDPG algorithm improves the power restricted autonomous sensors throughput. It is an enhancement over the DDPG algorithm since it manages experience more effectively. The CPDDPG approach uses that knowledge to guide the actor as they select the optimized course of action by employing a critic to estimate the value function. The technology effectively reduces energy consumptions and a result increased data throughput. Assumptions and notations that we have used in our research methodology or research paper for the development and study of proposed protocol, we make the following assumptions. The network devices are identical and consume the same amount of energy. All devices use the recommended communication protocols. The channel conditions remain constant within the time slot. Even if they changed from one time slot to the next, the devices are perfectly in synchronization with the other devices. So using the system design, we provide a method for developing the testing and the proposed communication protocol. The success of protocol in controlling the energy restrictions of IoT network and increasing data throughput will be examined further in the sections that follow. The algorithm of our work are listed over here. So playback buffer R must be launched. The first step. The second step to examine activities begin with a noise process and from the scratch. And the third step create a non-arbitrary process and for each episode actions explorations. So the fourth phase of this algorithm is initial observation state that we call H1. So after the next step, after each step based on the present policy and exploration noises, choose the best course of action that we call AT. So that is equal to SD divided by NT. So in the DDPG framework, the state space and the action space are crucial aspects that define the environment in which the agent operates. That entire set of possible sets that an agent can be in is referred to as its state space. So ST, that is the state space, represents the state at a time t. Then S is equals to S1, S2, S3, and so on to ST, represent the state space at different timing. So simulation step, if I talk about that, so in the experiment environment, the simulation for our proposed protocol was conducted in a synthetic environment modeling a large scale of IoT network. The network was composed of multitude of homogeneous sensors with a similar power constraint, each possessing the ability to communicate with others and with a central gateway. The communication range interface level and the noise level were set according to the typical real-world IoT network conditions. The DRL agent had enough time to learn the optimum course of action because there were enough episodes of simulation running at once. Now the performance metrics for our work, the major indication of how well the proposed communication protocol performed were energy efficient and throughput. To calculate energy efficiency, the sensor total energy consumption was divided by the volume of data successfully delivered. Throughput, on the other hand, was determined by how much data was successfully transmitted per unit of time. So resultant discussion that we can see. So there are three algorithms: CER, DDPG, and stochastic. So here we can see the stochastic in context of episode and throughput, stochastic is performing better than the remaining algorithms. So figure so like this figure show that the proposed CER-DDPG based protocol consistently outperforms the standard DDPG and the stochastic protocol in terms of energy efficient across episodes. So this demonstrates the protocol capacity to efficiently manage the finite energy resources of Internet of Things devices while ensuring high throughput. So because of it proposed improved performance, the CE DDPG based protocol appears to be a good alternate for improving communication in energy constant IoT network. The term data is used in a plural form. Power constant have a significant impact on how well the communication mechanism of IoT network perform. Given the limited power resources available to IoT devices, it is vital to design communication protocols that maximize data transformation efficiency while minimizing power constraint. So in the conclusion of our research work, so this study successfully demonstrated the effects efficiency of a novel DRL-based communication protocol in managing communication in energy-constrained IoT network by incorporating the SCMA strategy, CDMA architecture, and the CER-DDPG algorithm. Our proposed protocol outperformed traditionally DDPG and stochastic algorithm in terms of throughput and energy efficiency. The CER-DDPG based protocol adapted to power constraint more effectively and maintained higher throughput level even with increasing network size. So these results underline the potential of reinforcement learning, particularly the CERDDPG algorithm in solving complex IoT communication challenges. Our research also underlined the need of continued exploration of DRL methodologies to devise energy efficient high performance communication protocol for IoT network. Further work can focus on defining and expanding the proposed protocol, testing it on device IoT applications, and optimize its performance for real-time development. So it was the conclusion of our work. So thank you very much. Thank you.